Welcome to SPAN's Hidden Superpowers, unlocking ultimate CSAS performance beyond slicing. Today, we'll explore advanced techniques to maximize CPUT memory efficiency, going beyond traditional slicing methods. Our agenda includes understanding SPAN and its core concepts, advanced memory manipulation techniques, hidden methods beyond slicing, performance optimization strategies, and best practices for future directions. SPAN is a stack-only type introduced to enhance memory safety and performance. It reduces heap allocations, ensures type safety, and provides efficient access to contiguous memory segments, optimizing application performance. SPAN ensures memory safety by preventing out-of-bounds access, offering controlled memory management. Operating on stack memory reduces heap allocations, minimizing garbage collection and enhancing application performance. SPAN enables efficient data slicing of arrays, buffers, and strings without additional allocations. However, as a ref structee, it cannot be boxed or stored on the heap, limiting its use in async methods and class fields. SPAN provides a way to manipulate buffers without data copying, improving memory efficiency. Efficient memory reuse reduces overhead and boosts performance, especially in networking and I/O applications. Stackalloc allocates memory directly on the stack, offering faster access and release compared to heap allocation. SPAN works with Stackalloc for safe, efficient manipulation of temporary data buffers, enhancing performance. SPAN enables safe reinterpretation of memory as different data types, enhancing flexibility. Memory Marshal APIs offer tools for advanced memory manipulation, ensuring safety and performance when handling raw data. SPAN's index of method efficiently searches for a value, minimizing memory allocations. Last index of supports reverse pattern matching, while sequence equal compares spans for equality, enabling precise pattern matching. SPAN allows efficient handling of data segments without extra allocations. UTF-8 parser and UTF-8 formatter APIs enhance parsing and formatting, improving memory usage and throughput in data processing. SPAN enables direct operations on memory segments without copying data, enhancing algorithm speed. Zero-copy techniques reduce overhead, while optimizing CPU cache usage for faster data access and execution. SPAN operates on stack or unmanaged memory to reduce heap allocations, improving memory efficiency. Lowering heap allocations minimizes garbage collection frequency, enhancing application responsiveness. SPAN provides references to memory segments without copying data, enabling efficient data access. Zero-copy techniques are crucial for high-throughput systems like networking and real-time data processing. Micro-benchmarks show SPAN delivers significant speed-ups compared to traditional methods. It enhances memory efficiency, with real-world scenarios confirming its advantages in performance and memory handling. Improper use of SPAN in asynchronous operations can lead to runtime errors. Storing SPAN on the heap violates its ref struct restrictions. Understanding SPAN's nature helps avoid misuse and ensures safe memory handling. SPAN integrates efficiently with arrays, strings, and memory, enabling safe and fast access in .NET applications. It facilitates flexible memory management across asynchronous operations, improving performance. SPAN is becoming integral in CSAS, with updates enhancing its capabilities. Future CPOW standards aim to improve SPAN's flexibility, allowing greater adaptability in memory handling and boosting application performance. In conclusion, SPAN enables advanced memory manipulation, optimizing performance and promoting safer code practices. It maximizes application efficiency, reducing common memory errors and enhancing reliability.